So imagine you are standing outside just a massive, impenetrable bank vault.
Okay, I'm picturing it.
Right. You're looking at this 3-foot thick titanium door. You've got biometric retinal scanners, armed guards pacing the perimeter. I mean, you feel entirely safe.
You'd think so, yeah.
But what if the architectural blueprints to the building show a forgotten, unmonitored ventilation shaft running right through the foundation, like completely bypassing that vault door?
Well, then your titanium door is basically useless.
Exactly. You can have the strongest cryptographic vault in the world, but if you don't understand the highways, the hidden pathways, and the structural infrastructure beneath it, your data is already compromised.
And, the industry actually calls that a false sense of security based on perimeter obsession.
Perimeter obsession, I like that.
Yeah, it's a huge problem. If you want to protect data in transit, you really have to understand the fundamental physics and the logic of the roads it travels on. You have to trace how the invisible electrical voltages get from, say, a compromised laptop in a coffee shop to a server in a fortified data center. And you have to analyze all the architectural checkpoints they hit along the way.
Which is exactly why today we are tearing through a dense stack of architectural white papers, the official CISSP design notes, and some really recent postmortem research on infrastructure breaches.
It's a lot of material.
It is, but we're doing it to completely master Domain 4 of the official CISSP common body of knowledge. This is communication and network security, which, makes up roughly 13% of the exam.
Which is a massive chunk.
Huge. But more importantly, it is the literal blueprint of that bank vault we were talking about.
Yeah, definitely.
We are sitting down to really reverse engineer the backbone of logical infrastructure. So let's just start at the very foundation. The theoretical models that dictate how disparate hardware systems even establish a common language.
Right. So we had to talk about the OSI model and the TCP/IP model.
Yeah, diving right in.
So the Open Systems Interconnection Model, or OSI, is that classic 7-layer theoretical framework. Networking has relied on it for decades.
Right. It's practically ancient in tech years.
It is, but it forces engineers to modularize communication.
Yeah.
It starts at the top with layer 7, the application layer, where the user interface actually resides.
And then cascades all the way down to layer 1, the physical layer, right? Which just handles raw electrical signaling.
Exactly, just voltages on a wire.
I always conceptualize the OSI model as this highly paranoid corporate mailroom.
Well, that's a good way to look at it.
Right, because when you write a message at layer 7, it doesn't just go out the door. As it passes down through layer 6, which is presentation, and layer 5 session, the mailroom applies specific headers.
Like instructions for the receiving mailroom.
Exactly, instructions on how to decrypt, format, and maintain the connection. And by the time it hits layer 4, transport, it's put in a specialized envelope, and then into a routing box at layer 3 network, and finally a shipping crate at layer 2 data link.
And that mechanism is called encapsulation. It ensures each layer only interacts with its direct counterpart on the receiving end.
Right.
And the de-encapsulation process on the receiving side is equally rigid. The physical layer receiver doesn't care about the application data at all.
It just wants the shipping instructions.
Exactly. It only reads the layer 2 shipping crate instructions, strips them off, and passes the inner box up the chain.
Right.
And because of this rigid structure, the data payload actually changes its formal definition, its network container name, depending on where it sits in the stack.
Okay, so let's break those down because I know that's crucial. At the application, presentation, and session layers, so layers 7, 6, and 5, we refer to the payload simply as a protocol data unit, or PDU.
Right, PDU. But the moment it hits layer 4, the transport layer, the terminology shifts based on the specific protocol being used.
Okay, so if we are using TCP, which guarantees delivery through constant acknowledgments, what happens?
Then that PDU is chopped up and encapsulated into a segment.
A segment. Got it. But what if we're using UDP? Which is, connectionless, fire and forget, usually for streaming video or voice.
And then becomes a datagram?
Segment for TCP, datagram for UDP.
Exactly. From there, layer 3, the network layer, adds the logical IP routing headers. That transforms the segment or datagram into a packet.
Right. We hear packet all the time.
Yeah, it's the most common term. Then as it moves down to layer 2, the data link layer, the local hardware MC addresses get appended, and that creates a frame.
Frame at layer 2.
Yeah. And finally, the network interface card translates that frame into layer 1 raw bits. So just high and low electrical voltages or pulses of light over a fiber medium.
Okay, I have to challenge the actual utility of the OSI model here, though. I
Yeah.
mean, modern networks run exclusively on the TCP/IP suite.
Pretty much, yeah.
And TCP/IP collapses this whole thing down to 4 functional layers: application, transport, internet, and link. So does anyone actually use the OSI model in the real world anymore, or is it just an academic torture device for exams?
I hear that a lot. And yes, the TCP/IP model absolutely dictates the functional protocol suite of the modern internet.
Right.
But the OSI model endures because it provides a granular, universal diagnostic language for engineers.
Oh, I see.
Yeah, so when a network architect said, hey, we have a layer 2 issue, every engineer in the room instantly knows we are looking at switches, MC addresses, and frames.
Ah, so you aren't wasting time looking at layer 3 IP routing tables or layer 7 application firewalls.
Exactly. It isolates the fault domain instantly. It's the lingua franca of troubleshooting.
That diagnostic precision makes total sense. So speaking of layer 3 IP routing, we really need to examine the transition occurring at the internet layer of the TCP/IP model.
You mean the shift from IPv4 to IPv6?
Yeah, because it isn't just a simple software upgrade, right? It's a fundamental overhaul of how we address nodes on a network. IPv4 relies on a 32-bit addressing scheme, capping out at roughly 4.3 billion unique addresses.
Which the global internet exhausted years ago.
Yeah.
And we've kept IPv4 on life support using network address translation or NAT, but the architectural debt is just immense.
Right, NAT is everywhere, but IPv6 solves this by moving to a 128-bit addressing scheme.
The scale of that is difficult to even comprehend. It provides enough unique, routable IP addresses to assign one to every single atom on the surface of the Earth.
Which is mind-blowing. But because we are still deeply mired in IPv4, engineers spend massive amounts of time manipulating subnet masks just to conserve addresses.
Right, constantly. We use CIDR notation for that. Classless interdomain routing.
Okay, so when you see an IP address followed by slash, like 192.168.1.024.
Right, that 24 is an explicit instruction to the router. It states that the first 24 bits of the 32-bit address are strictly locked to identify the network itself.
Leaving precisely 8 bits available to assign to individual hosts on that network.
Exactly. 2 to the power of 8 gives you 256 addresses. You subtract 1 for the network identifier and 1 for the broadcast address, which yields 254 usable host IPs on that specific subnet.
And this mathematical boundary prevents a single network segment from growing so large that broadcast traffic just completely overwhelms the bandwidth.
Exactly. It keeps the collision domains manageable.
There are also automated fail-safes baked into these addressing schemes, aren't there? Like in IPv4, if a device boots up, sends out a DHCP request, and just hears nothing back.
Yeah, that triggers APIPA, or automatic private IP addressing.
Right, so it assigns itself a pseudo-random address in that 169.254.x.x range.
Yeah, it's essentially the device throwing its hands up and saying, well, I have no authoritative controller, so I'm generating a temporary local badge just to talk to anything plugged into my immediate switch.
It's a clumsy but necessary failover. But IPv6 handles network entry with far more sophistication, doesn't it?
Oh, absolutely. Through SLAA, which is Stateless Address Auto Configuration.
Stateless meaning it doesn't need a DHCP server keeping a state table of who has what IP.
Exactly. An IPv6 device doesn't need a central DHCP server at all. It just listens to local router advertisements, grabs the network prefix, and mathematically combines it with its own hardware MAC address.
Wow, so it instantly generates a globally unique, fully routable IPv6 address entirely on its own.
Yep, completely autonomously.
Okay, so let's track how the traffic actually traverses these networks once all these addresses are established. The routing logic relies on 4 primary transmission modes, right?
Right.
Unicast is the standard one-to-one communication, like a single client laptop opening a direct session with a specific web server.
And then you have broadcast, which is one-to-all. That's a node shouting a packet to every single interface on its local subnet boundary.
Which is noisy.
Very noisy. Then multicast introduces selective efficiency, so one-to-many, but strictly for devices that have explicitly subscribed to an IGMP multicast group.
Okay, so like a stock ticker feed or a corporate video broadcast.
Right. The server only sends one stream, and the intermediary routers duplicate the packets only down the paths where active subscribers live.
That saves a ton of bandwidth. And finally, Anycast is one to nearest, right?
Yes. A global network might have 50 DNS servers sharing the exact same Anycast IP address.
So the Internet's core BGP routers calculate the shortest topological path and seamlessly direct your query to the server geographically closest to you.
Exactly, which drastically reduces latency for the user.
Okay, but standard IP traffic, whether it's Unicast or Anycast, usually flies across the backbone routers in plain text.
It does, which is terrifying.
Right. Any compromised node sitting in the path can execute packet captures and read the payloads. So to secure data in transit, we have to look at the heavyweight cryptographic suite, which is IPsec.
Yeah, IPsec is foundational. It operates right at layer 3, meaning it protects everything above it, so TCP segments, UDP datagrams, and all the application payloads.
But IPsec is notoriously complex.
It's very complex. Its complexity lies in its modularity. You really have to strictly differentiate between its operational modes and its cryptographic protocols.
Okay, let's start with the modes. Transport mode versus tunnel mode.
Right. Transport mode is the default for host-to-host communication. It encrypts only the payload of the packet. The original IP header remains completely intact and visible in plain text.
Because the intermediary routers along the path still need to read the source and destination IPs to route the packet, right?
Exactly. But if you are connecting two remote corporate sites over the public internet, leaving those internal IP headers visible exposes your entire internal network topology to an adversary.
That's a huge vulnerability, so that dictates the use of tunnel mode.
Yes, tunnel mode takes the entire original packet payload, internal IP headers, everything, encrypts it, and encapsulates it inside a brand new IP packet with a completely different header.
So the intermediary internet routers only see the new headers, which just point from the public firewall of site A to the public firewall of site B.
Exactly. They have zero visibility into the internal client IPs communicating inside the tunnel.
Okay, so that covers the modes. Now, regarding the cryptographic heavy lifting inside those modes, IPsec relies on two primary protocols, AH and ESP.
Right. AH, or authentication header, provides strict data integrity and source authentication using cryptographic hashing. It guarantees the packet wasn't altered in transit.
I always view AH as a tamper-evident wax seal on a clear envelope. You know exactly who sent it, and you know it hasn't been opened, but the contents are still completely visible to anyone looking.
Because AH provides zero encryption.
Right. No confidentiality at all.
For confidentiality, you need ESP, the encapsulating security payload. That's the locked titanium briefcase. ESP provides robust symmetric encryption for total confidentiality, alongside limited integrity checks.
And to establish these secure tunnels dynamically in the first place, the routers utilize IKE, right? The Internet Key Exchange.
Yes, IKE, which relies heavily on ISAKMP.
The Internet Security Association and Key Management Protocol.
That's a mouthful, but yeah. It governs the complex mathematical handshakes, where two untrusted peers negotiate encryption algorithms and securely exchange Diffie-Hellman keys over a hostile medium before any actual data is ever sent.
Wow. Okay, so that's layer 3, but we layer additional security protocols higher up the stack, too.
We have to. At layer 7, we rely on SSH, Secure Shell, to provide encrypted terminal access to infrastructure, totally replacing the ancient plaintext Telnet protocol.
Telnet is a nightmare. And for web traffic, we use SSL and its modern successor, TLS, to establish encrypted web sessions.
Right. And for internal identity management, we heavily deploy Kerberos,
which operates on a complex system of granting tickets, right, to authenticate users to services without ever transmitting their actual password hash over the wire.
Exactly. And those standard protocols are really well understood. The true architectural nightmare emerges when we look at converged protocols.
Converged protocols. So convergence is the practice of taking highly specialized, historically isolated infrastructure traffic and encapsulating it within standard TCP/IP to run over generic Ethernet hardware.
Yes, exactly. Like FCO, Fiber Channel over Ethernet, or iSCSI.
Right, because historically, a data center had a dedicated physically air-gapped network just for raw block-level storage traffic.
But by moving that storage traffic onto the same Ethernet switches handling standard user web browsing and email, we break physical isolation just to save money on cabling and hardware.
The economic incentive is massive, but the security risk seems severe.
It is severe, because if a threat actor compromises a low-privileged workstation and the converged network isn't flawlessly partitioned, the attacker can execute VLAN hopping.
Or packet sniffing to intercept raw database read and write commands.
Exactly. And this convergence extends to voice communications too, with VoIP, voice over IP, and high-speed data interconnects like Compute Express Link.
Securing VoIP requires specialized cryptographic overlays, doesn't it? Because standard IPsec is often too heavy and introduces latency into the voice call.
Right. Nobody wants a 2-second delay on a phone call. Instead, we secure the call setup and signaling using SIPS, Secure Session Initiation Protocol.
And once the phones mathematically agree on the parameters, the actual digitized audio and video data stream is encrypted using SRTP, the Secure Real-Time Transport Protocol.
Exactly. But cryptographic overlays aren't enough. When you mix highly sensitive storage traffic, real-time voice, and standard user data on the same copper and fiber, you must enforce rigorous logical boundaries.
Which makes network segmentation the most critical defense mechanism in modern architecture.
Absolutely.
Physical segmentation is the legacy approach, right? Literally buying separate switches and running separate cables for different security zones.
Yeah, it's how we execute out-of-band management, where administrators use a dedicated, physically isolated management network to access router command line interfaces.
Right, ensuring management traffic never touches the user network. And the extreme end of physical segmentation is an air-gapped network, like a nuclear centrifuge control system, completely severed from external connectivity.
But physical segmentation is operationally inflexible and financially prohibitive at scale for most companies. Consequently, architectures rely on logical segmentation.
So carving up a single physical layer 2 switch into multiple virtual local area networks, or VLANs, creating isolated broadcast domains.
And we also deploy virtual routing and forwarding, or VRF, to run multiple, completely segregated Layer 3 routing tables simultaneously on a single physical router.
But the threat landscape has evolved way beyond basic VLANs. I mean, if an attacker breaches an endpoint via a phishing payload, and that endpoint sits inside a standard 24 VLAN,
then the attacker has unobstructed, uninspected lateral movement to 253 other machines in that exact same broadcast domain.
and the traditional perimeter firewall is totally useless there because the traffic never actually leaves the VLAN to hit the firewall.
Exactly. This failure of perimeter defense necessitates microsegmentation.
Which is really the architectural manifestation of the zero trust philosophy.
It is. Instead of relying on a massive firewall at the edge of the network, we push security policies all the way down to the hypervisor level.
So wrapping a virtual stateful firewall around every single virtual machine and container in the data center.
Right. So even if a web server is fully compromised, the hypervisor's microsegmentation policy mathematically drops any unauthorized traffic attempting to traverse to the database server sitting on the exact same physical blade.
But managing 10,000 individualized micro-firewalls through manual command line configuration is impossible.
Oh, completely. The only way to orchestrate microsegmentation at scale is through software-defined networking, or SDN.
And SDN fundamentally alters the anatomy of networking hardware, doesn't it?
It does. In a traditional architecture, a physical router houses both a control plane and a data plane.
The control plane being the CPU and the routing intelligence, it builds the routing tables, processes BGP updates, calculates the optimal paths.
All right, and the data plane is the custom ASIC hardware, the muscle, that actually inspects the incoming packet headers and physically forwards them out the correct port at wire speed.
Okay, so SDN decapitates the router, completely decouples the routing intelligence from the physical hardware.
We extract the control plane from all the individual switches and centralize it into a cluster of SDN controller service.
So the physical switches left in the racks are reduced to just high-speed, dumb data planes. They no longer make independent routing decisions at all.
Right. When a physical switch receives a packet it doesn't recognize, it queries the central SDN controller. The controller dictates the rules via southbound interfaces, utilizing flow table protocols like OpenFlow to push routing instructions down to the hardware.
Okay, so southbound talks to the hardware. Conversely, the central controller exposes northbound interfaces, usually RESTful APIs, up to security applications, orchestrators, and automated billing systems.
Exactly. North to software, south to hardware. And when you abstract the control plane across geographically dispersed branch offices over the public internet, you create an SD-WAN, a software-defined wide area network.
Which dynamically measures latency and packet loss across multiple commodity broadband and cellular links, constantly rerouting application traffic to optimize performance without human intervention.
It's incredibly efficient. But this abstraction introduces a terrifying single point of failure.
Right, because if an advanced persistent threat, an APT, compromises the SDN controller's northbound API.
They don't just own a single router. They instantly dictate the flow of every packet across the entire global enterprise infrastructure.
Wow. Okay, so we have exhaustively mapped the wired architecture. but the perimeter dissolves entirely when we introduce wireless and cellular communication.
Yeah, the physical boundary of a building no longer confines the network signal.
So let's analyze 802.11 Wi-Fi security, which is essentially a 25-year history of cryptographic failures and software patches.
It really is. The original standard, WEP, wired equivalent privacy, was catastrophic.
Right. It relied on the RC4 stream cipher, but implemented initialization vectors, or IVs, that were only 24 bits long, and transmitted in plaintext.
Which is a huge flaw. A busy access point would reuse the same IV rapidly, allowing an attacker capturing packets in the parking lot to mathematically deduce the static encryption key in under 10 minutes, using simple statistical IV attacks.
Just a total failure. Then came WPA, Wi-Fi Protected Access, which was a rabid software patch that introduced TKP to dynamically change keys.
But it still relied on the flawed RC4 cipher. WPA2 was the true structural upgrade, mandating AES encryption.
However, WPA2's pre-shared key mode, which every home and small business used, possessed a devastating vulnerability, and it's a four-way handshake.
Yeah. When a client authenticates to a WPA2 access point, the cryptographic handshake is broadcast over the air. An attacker can execute a targeted deauthentication attack, forcibly disconnecting a legitimate user.
And when the user's device automatically attempts to reconnect, the attacker captures the four-way handshake.
Exactly. Then they leave the area, take that packet capture to a high-powered GPU rig, and run an offline dictionary brute force attack.
Just hashing millions of password guesses a second against the captured handshake until they find the match.
Yep. So WPA3 fundamentally neutralizes the offline dictionary attack by eliminating the standard four-way handshake in favor of SAE simultaneous authentication of equals.
Right, and SAE utilizes a zero-knowledge proof mechanism called the Dragonfly key exchange.
The cryptography in Dragonfly forces the client and the access point to perform complex elliptic curve mathematics to prove they both know the password without ever actually transmitting a hash of the password itself over the air.
Crucially, the math requires live interaction for every single authentication attempt. You cannot capture a WPA3 handshake and brute force it offline.
Right. You must interact directly with the router for every single guess, which makes brute forcing computationally infeasible.
But for an enterprise environment, relying on a single shared password, even with WPA3, is architectural malpractice, right?
Oh, absolutely. If an employee leaves, you'd have to change the password on 1,000 devices. Enterprises require 802.1x port-based access control.
So 802.1x acts as an authentication proxy.
Yes. When a corporate laptop attempts to associate with a wireless access point, the access point blocks all network traffic except for EAP, the Extensible Authentication Protocol.
The laptop sends its individual user credentials or a digital certificate via EAP to the access point,
which then forwards them directly to a back-end Radius authentication server. Only if the Radius server mathematically validates the specific user's identity does the access point open the logical port and permit network traffic.
And wireless risk extends far beyond Wi-Fi. We also have to factor in cellular and satellite architecture. Cellular networks have evolved rapidly through 4G LTE to 5G, pushing bandwidths up to 10 gigabits per second, and 6G research is already underway.
The security implication of 5G isn't the cryptography of the air interface itself. It's the architectural bridging.
What do you mean by that?
Well, high-speed cellular networks allow end users to trivially bypass multi-million-dollar corporate firewalls.
Oh, right. If an employee enables a 5G mobile hotspot on their corporate laptop while connected to the internal LAN,
they have just built an unmonitored high-speed bridge directly from the hostile public internet into your core network.
That is terrifying. And what about satellite communications? They're increasingly leveraged for SD-WAN backhaul in remote locations, but architects must calculate orbital physics there.
Yeah, GEO, geostationary orbit satellites, sit roughly 35,000 kilometers above the equator. The speed of light dictates a minimum round-trip latency of 500 to 600 milliseconds.
Which will break timing-sensitive applications. MEO, medium Earth orbit, cuts that latency down somewhat.
And LEO, low Earth orbit constellations like Starlink, orbit at just 500 kilometers, delivering fiber-like latency.
However, because they are moving so fast relative to the Earth's surface, the ground antenna must constantly execute complex, cryptographically secure handoffs between dozens of different satellites passing overhead every hour.
It's an incredible engineering feat, but but a huge security challenge.
Before we leave wireless entirely, I have to address personal device security regarding Bluetooth because the attack vectors there are well documented.
Yep, Bluetooth is everywhere.
Right. So we have Bluesniffing, which is passive eavesdropping on unencrypted Bluetooth signals, and Bluejacking, which involves sending unsolicited messages or vCards to a device, exploiting lax pairing settings.
Right, but those are mostly nuisances. Bluesnarfing is the active theft of data.
So an attacker pulling down contact lists, emails, or text messages from a vulnerable device over a Bluetooth connection without user interaction.
Exactly. And the most severe vector is bluebugging, where the attacker leverages firmware vulnerabilities to install a backdoor. They gain complete remote command and control over the device to secretly record audio or route phone calls.
Wow. So what's the primary mitigation strategy?
Rigid configuration management. Disabling Bluetooth when not in active use, enforcing non-discoverable modes, and explicitly prohibiting the use of legacy devices that rely on default pairing pins like 0000.
Okay, this transitions us directly from the ephemeral transmission of data to the tangible checkpoints that govern it. Let's shift our analysis to Module 2, Secure Network Components.
Because protocols are just ghosts without physical hardware pushing them forward.
Exactly. If I'm an adversary, I might not attempt to crack your WPA3 encryption or reverse engineer your IPsec tunnels. I might simply target the physical layer, the transmission media, and the hardware processing the logic.
The physical layer really is the circulatory system of the architecture. Wired transmission media dictates both bandwidth capacity and physical vulnerability.
We rely a lot on twisted pair copper cabling, right? STP, shielded twisted pair, and UTP, unshielded twisted pair. These are your standard Cat6 cables.
Right. The copper wires are twisted at specific geometric intervals to physically cancel out electromagnetic interference, or crosstalk, from adjacent wires.
And STP wraps the pairs in metallic foil for deployments in highly noisy industrial environments.
Legacy environments still harbor coaxial cable too, the old thinnet and thicknet standards, which use a central copper core surrounded by heavy insulation and a braided shield.
But the backbone of all modern high-speed architecture is fiber optic cabling.
Absolutely. Fiber optics abandon electrical signaling entirely, transmitting data via microscopic pulses of light down a glass core.
Which makes fiber completely immune to electromagnetic interference, right? And significantly hardens it against physical wiretapping.
Exactly. An attacker cannot simply induce an electrical current to sniff packets on fiber. They must physically splice the glass. And doing that disrupts the light path and triggers immediate alarms.
The true magic of fiber, though, is how we maximize its throughput using DWDM, dense wavelength division multiplexing.
DWDM relies on the physics of chromatic dispersion. It takes up to 80 different distinct wavelengths, or colors, of laser light, modulates an independent data stream onto each color, and fires them all down the exact same microscopic strand of glass simultaneously.
And because the wavelengths don't interfere with each other, a single cable can push terabits of data per second.
It's amazing. But optical fiber can still be severed by a backhoe outside, and high-end core routers experience hardware failures. A secure architecture mandates systemic equipment redundancy.
Meaning deploying dual redundant power supplies connected to separate grids, redundant core routers, overlapping switch fabrics.
And we manage this redundant hardware layer through sophisticated load balancing architectures. A Layer 4 or Layer 7 load balancer acts as a traffic cop, distributing incoming TCP sessions across a massive farm of back-end web servers.
When designing the redundancy of the load balancers themselves, architects usually choose between active-active and active-passive models.
Right. In an active deployment, all redundant hardware units are simultaneously processing traffic. This maximizes your return on hardware investment and provides the highest possible aggregate throughput.
However, the architectural danger lies in capacity planning. If you are running two routers in active-active, and they are both operating at 60% CPU utilization, a hardware failure in router A will force 100% of its traffic onto router B.
Which means router B instantly spikes to 120% capacity, fails, and causes a cascading network outage.
And that exact scenario dictates the use of active-passive configurations for critical bottlenecks.
Yes. The primary device handles 100% of the traffic load. The passive secondary device sits completely dormant, doing nothing but listening for a cryptographic heartbeat signal from the primary.
If the primary goes offline, the passive unit instantly assumes the primary's IP and MAC addresses and takes over the load. You're paying for hardware that sits idle, but you guarantee sufficient capacity during a failover state.
But having redundant pathways is totally useless if malicious devices are allowed to connect to them. This requires network access control, or NAC.
An NEC system basically operates as an architectural immune system, right? When a foreign entity, a device, attempts to attach to the network tissue, the NEC system interrogates its biological markers before granting it an IP address.
I love that analogy. And this interrogation relies on two distinct deployment philosophies. Pre-admission NAC is the strict gatekeeper.
So before a device is allowed to communicate with internal servers, the NAC system mandates a posture assessment.
It asks, is your operating system fully patched? Is your endpoint protection platform running? Are your antivirus definitions less than 24 hours old?
If the device fails any of these checks, the NAC system dynamically assigns the switch port to an isolated quarantine VLAN, where the device can only access a remediation server to download the required patches.
But passing a point-in-time check at 9:00 a.m. doesn't guarantee the device won't be compromised by a zero-day exploit at noon.
Right. Which is where post-admission NAC comes in. It assumes the device is volatile.
It continuously monitors the device's behavioral telemetry after it has been granted access, enforcing an authorization matrix.
So if a marketing laptop suddenly initiates an SSH brute force attack against a database server, the post-admission NAC system instantly revokes the authentication token and drops the device off the network.
Exactly. And implementing this immune response requires telemetry collection mechanisms. Agent-based NAC deployments rely on specialized software installed directly on the operating system of the endpoint.
This agent constantly reports deep system state metrics back to the NAC controller.
We use permanent agents for corporate-owned devices and dissolvable agents, temporary applets that execute during the login process, assess the machine, and delete themselves for contractor laptops.
However, you cannot install a software agent on an internet-connected thermostat or a proprietary medical imaging machine.
No, you can't. For IoT and specialized hardware, architects deploy agentless NAC. Agentless systems rely on the network infrastructure itself, the switches and routers, to passively profile the device based on its MAE address vendor ID, DHCP request fingerprints, and traffic flow patterns.
To deduce its identity and assign appropriate access policies without any software on the device.
Right. And for human-driven guest access, we leverage the captive portal,
which intercepts the user's initial HTTP request at the gateway, forcibly redirecting their browser to an authentication page or terms of service agreement before the firewall permits routing to the broader internet.
Speaking of firewalls, the firewall remains the foundational access checkpoint, but its mechanisms have evolved drastically over the years.
Definitely. Early stateless packet filtering firewalls were incredibly fast but critically blind. They only examined the source IP, destination IP, and port number of individual packets, completely unaware of the broader conversation.
Right. A stateless firewall could block traffic on port 23, but it couldn't tell if an incoming packet on port 80 was a legitimate response to an internal user's web request or a completely unprompted inbound attack.
And that failure led to stateful inspection. A stateful firewall maintains a dynamic state table in its memory, tracking the three-way TCP handshake, SYN, SAYUP, ACK.
It understands the context of the connection, ensuring that incoming traffic is exclusively permitted if it is part of an established, internally initiated session.
But stateful firewalls only inspect up to Layer 4. To stop sophisticated application layer attacks, we deploy application-level proxies.
A proxy fundamentally breaks the TCP connection. When a client wants to reach a server, it connects to the proxy first.
The proxy terminates the connection, deeply inspects the Layer 7 payload for malicious commands, and if it's clean, the proxy initiates a brand new, separate TCP connection to the destination server on behalf of the client.
And circuit-level gateways operate on a similar proxy methodology, but at Layer 5, the session layer, focusing on validating the session setup rather than inspecting the deep application payload.
In modern enterprise architecture, we don't rely on a single firewall. We implement multi-tiered firewalls from different vendors to establish distinct security zones.
Recognizing that a zero-day vulnerability in vendor A's firewall won't immediately compromise vendor B's firewall sitting right behind it.
Exactly. And at the very edge of the application layer, we deploy the WF, the Web Application Firewall.
Right, a standard stateful firewall sees port 443 HTTPS traffic and permits it. A WAF actually terminates the TLS encryption, decrypts the HTTP payload, and parses the syntax of the web request.
Specifically searching for application logic exploits like SQL injection or cross-site scripting payloads before they can even hit the web server backend.
Yet despite this massive investment in network perimeter checkpoints, the architectural reality of a highly mobile, cloud-integrated workforce dictates that the network perimeter is highly porous, if not completely dead.
Which forces a massive pivot toward host-based endpoint security. We really must architect our systems under the assumption that the network is already breached and hostile.
This assumption drives the modern endpoint security stack. Traditional signature-based antivirus is totally obsolete. We deploy EPP, endpoint protection platforms,
Which utilize machine learning heuristics to analyze the behavior of executables in real time, proactively attempting to block fileless malware and ransomware from executing in memory.
but prevention algorithms eventually fail against an advanced persistent threat, an APT. That inevitability requires the deployment of MDR and XDR managed detection and response and extended detection and response.
These platforms operate under the assume breach paradigm. They don't just try to block execution. They continuously stream deep system telemetry process executions, registry modifications, network connections to a centralized data lake.
And XDR algorithms correlate telemetry from the endpoints, the firewalls, the cloud identity providers, and the email gateways to detect the faint, distributed behavioral indicators of an attacker attempting lateral movement.
Because analyzing this massive data stream requires a 234/7365 Security Operations Center staffed by Tier 3 threat hunters, organizations frequently outsource the monitoring to an MSSP, a managed security service provider.
The endpoint is the final perimeter, which brings us to Module 3, Secure Communication Channels.
Right. We have established the secure architecture and deployed the hardened components. But an organization must function in the real world. We have to securely extend this fortress to a remote workforce, network administrators, and third-party telecom vendors without compromising the core.
The most robust method for securing remote access is to completely abstract the data away from the physical endpoint device.
So if an employee connects from a personal, unmanaged laptop over a hotel Wi-Fi network, we cannot trust the integrity of their operating system.
We can't. Instead of establishing a VPN that places their untrusted device directly onto our corporate LAN, we deploy VDI, Virtual Desktop Infrastructure, or VMI, Virtual Mobile Interface.
In a VDI architecture, the actual Windows desktop operating system, the sensitive corporate applications, and the proprietary data files never leave the secure servers running in the corporate data center, right?
Exactly. The remote user's laptop functions merely as a dumb terminal. The VDI client establishes an encrypted session that only streams the pixel updates of the screen to the remote user while transmitting their keystrokes and mouse clicks back to the data center.
So if the employee's laptop is stolen at an airport or infected with the destructive ransomware variant, the corporate data remains completely unaffected because no data was ever physically stored on the local hard drive.
Right. Now, for our internal network administrators, we require a different level of secure remote control. Admins utilize terminal emulation protocols like SSH to establish command line control over core routers and hypervisors.
However, an architect must never allow an administrator to SSH directly from their daily use workstation into a critical domain controller.
Oh, never. If the admin's workstation is compromised by a drive-by browser download, the attacker can hijack the SSH session and instantly pivot to the most sensitive infrastructure.
To sever that attack path, architects deploy jump boxes situated within screened subnets, historically referred to as DMZs. A screen subnet is a heavily monitored network segment sitting between two firewalls.
And a jump box is a hardened, highly locked down server residing in that subnet. It acts as a decontamination airlock.
So the administrator must first authenticate and establish an SSH connection from their workstation to the jump box.
The jump box strips away unnecessary protocols, executes strict session recording, and enforces multi-factor authentication.
And from that sterile jump box environment, the administrator initiates a second, distinct SSH connection to the sensitive internal router.
This architecture breaks the direct TCP connection, preventing malware on the workstation from bridging directly to the core infrastructure.
We control the jump boxes, but we do not control the Y-area network connections linking our branch offices. Organizations rely on backhaul networks provided by external telecommunication carriers, routing traffic over the PSTN, the public switched telephone network.
From an architectural standpoint, you must treat the telecom provider's infrastructure as entirely untrusted and potentially compromised. Every byte of data traversing a third-party leased line must be heavily encrypted via IPsec VPNs.
And establishing secure communications with third-party vendors requires more than just cryptography. It requires formalized legal and technical governance. Before a packet ever crosses the wire between two distinct corporate entities, management must negotiate an MOU, a Memorandum of Understanding.
The MOU outlines the high-level business intent, the liabilities, and the overarching purpose of the data sharing.
The MOU establishes the legal framework, but it's insufficient for engineering. Engineers execute the ISA, the Interconnection Security Agreement.
Yes. The ISA is a highly prescriptive technical document that dictates the exact IP addresses allowed to communicate, the specific TCP port numbers that must be opened on the boundary firewalls, the exact cryptographic ciphers required for the VPN tunnel, and the incident response protocols if the link is compromised.
Okay, we have analyzed the theoretical models, the physical hardware, the cryptographic tunnels, and the access controls. But to truly master Domain 4 of the CISSP common body of knowledge, you have to understand how these disparate technologies interact dynamically during a crisis.
That's the real test.
To contextualize the remaining vocabulary in the official syllabus, we are going to reconstruct the anatomy of a sophisticated cyber attack, an APT, an advanced persistent threat breaching a modern enterprise network, analyzing the specific architectural components they exploit and the defenses they trigger at every step.
An APT operates with immense patience and technical precision. Phase 1 is always reconnaissance against the external perimeter. The attacker starts by analyzing the organization's boundary routers, the edge devices that advertise the company's public IP space to the internet via BGP.
Right, and to map the firewall rules without triggering intrusion detection alarms, the APT executes a TCP-ACK scan.
A standard TCP connection requires a three-way handshake, SYN, SYNAC, ACK. In a TCP-ACK scan, the attacker crafts a packet with only the acknowledgement flag set and fires it at the firewall.
The packet pretends to be the continuation of an already established conversation.
Exactly. By analyzing whether the firewall drops the packet, rejects it, or lets it through to a back-end server, the attacker can mathematically deduce the firewall's internal rule set without ever actually establishing a logged connection.
Simultaneously, the APT targets the organization's extranet, the portion of the private network securely opened up to specific partners. The extranet is typically protected by a gateway device, which translates protocols between disparate systems.
To disrupt the external application availability, the attacker might launch a teardrop attack. This is vicious denial of service technique, where the attacker sends heavily fragmented IP packets with intentionally overlapping offset values in the headers.
Oh, that's nasty. When the victim's concentrator or load balancers attempt to mathematically reassemble those overlapping fragments in memory, the operating system kernel gets hopelessly confused, triggering a kernel panic and a system crash.
But this APT is smarter. They want stealth. They target the naming infrastructure. They execute DNS poisoning.
Meaning they compromise a vulnerable DNS server and inject fraudulent records into its cache, quietly redirecting legitimate internal traffic meant for a corporate payroll application to an attacker-controlled IP address.
Even worse, if they gain access to the registrar level, they execute domain hijacking, legally transferring the ownership of the corporate domain name to themselves, granting total control over all inbound web and email traffic.
Assuming the APT identifies a vulnerability in a public-facing application hosted in the screened subnet, they attempt to exploit a race condition,
which is a highly complex software vulnerability where the application security mechanism depends on the precise sequential timing of database queries.
The attacker floods the application with simultaneous requests via an API, exploiting the microsecond gap between a balance check and a database write to bypass authentication and gain a shell on the web server.
With a foothold in the DMZ, Phase 2 begins, pivoting into the internal network. The APT needs to bypass the captive portal protecting the internal wireless network. They deploy a rogue access point, executing an evil twin attack.
They broadcast the exact same SSID as the corporate network, but with a stronger signal. To force clients to connect to it, they launch a disassociation attack, broadcasting forged management frames that forcefully kick legitimate laptops off the real network.
And when the laptops auto-reconnect, they hit the evil twin. The attacker captures the authentication handshake. They bypass legacy MAC filtering, which attempts to restrict network access based on hardware addresses by simply spoofing the MAC address of a captured legitimate device. They are now on the internal Layer 2 network.
Phase 3 is Layer 2 manipulation. The internal network is a massive collision domain, managed by switches acting as a bridge between segments. To intercept traffic, the APT executes ARP poisoning.
The ARP protocol translates Layer 3 IP addresses to Layer 2 MAC addresses, but it is entirely stateless and unauthenticated.
The attacker sends continuous forged ARP replies to the victim's laptop, mathematically associating the attacker's MAC address with the IP address of the core default gateway. The laptop's operating system updates its internal ARP cache with the lie.
Now, every single packet the victim tries to send to the internet is physically switched directly to the attacker's machine first, establishing a devastating man-in-the-middle position.
If the switch has hard-coded ARP inspection preventing that, the attacker pivots to CAM table flooding. The content addressable memory table inside the switch ASIC maps ME addresses to physical ports.
The attacker unleashes a script generating thousands of fake, randomized MAC addresses per second. The switch is extremely limited. High-speed ASIC memory fills up instantly.
And when a switch runs out of CAM memory, it panics. It defaults to a fail-open state to keep traffic flowing, reverting to the behavior of a primitive 1990s hub.
It stops intelligently switching packets and begins broadcasting every single incoming frame out of every single port simultaneously. The attacker just turns on a packet sniffer and vacuums up the entire subnet's traffic.
The APT uses this visibility to map the legacy infrastructure, identifying old mainframes using token passing networks instead of Ethernet's standard CISSP collision detection mechanisms.
They identify misconfigured trunk ports and execute VLAN hopping, using double-tagged 802.1q Ethernet frames to force the switch to bleed their packets out of the compromised guest VLAN directly into the highly secure server VLAN.
Now, deep in the core, Phase 4 focuses on infrastructure dominance. They target LDAP to dump the Active Directory database and RPC endpoints to execute remote code on domain controllers.
They manipulate SNMP, the network management protocol, to reconfigure core routers. They scan for legacy CDMA cellular modems attached to out-of-band management ports.
They need to establish a persistent, stealthy command and control channel out to the internet. They can't use standard ports because the multi-tiered firewall will block them.
Instead, they exploit tunneling. They encapsulate their malicious payloads inside ICMP ever requests, standard ping packets, which most firewalls naively permit outbound for diagnostic purposes.
Or they use GRE, generic routing encapsulation, or L2TP, layer 2 tunneling protocol, to build a hidden VPN tunnel straight through the firewall.
They assign themselves non-routable IP addresses behind NAT, network address translation, to obscure their internal movements from the perimeter NIDs, network intrusion detection systems.
They know the NIDS relies on network taps, while the HIDs, host intrusion detection systems, monitor the endpoints, so they utilize rootkits to blind the HID's telemetry.
Finally, Phase 5, exfiltration. To bypass the DMR, DKIM, and SPF email security validations, they don't try to spoof emails from the outside.
They compromise the internal exchange server and utilize the internal PKI infrastructure, controlled by the root of trust, to issue themselves a fraudulent X.509 certificate defined by the ITUT standards body.
They bypass the OCSP revocation checks, digitally sign their exfiltration emails using SMEN, and encrypt the transport layer using implicit SMTPS, pushing gigabytes of stolen intellectual property out of the network via an encrypted email channel that the DLP scanners cannot inspect. The attack chain is complete.
Analyzing that attack chain really demonstrates that securing a network requires a holistic mastery of how protocols, hardware, and access controls interact. And I want to leave you with a provocative thought regarding the future of this architecture. We discussed the massive industry shift toward SDN, NFV network function virtualization, and cloud architectures.
Right.
The entire physical infrastructure, the routers, the cables, the firewalls, is being completely abstracted away into software code.
Exactly. The abstraction layer itself is becoming our largest, most dangerous blind spot. If an attacker identifies a logic flaw in the northbound, southbound interfaces, or the API of a centralized SDN controller, they don't have to bother executing ARP poisoning or VLAN hopping.
Right. They don't compromise a single router. They instantly compromise the routing logic of the entire global infrastructure.
It's completely centralized risk.
When the architectural blueprints themselves are written in hackable code, the titanium vault door doesn't even matter anymore. Thank you for taking this deep dive into the official CISSP common body of knowledge with us. Keep interrogating the architecture around you, and we will see you on the next deep dive.